Yeah, very good afternoon, students. Good afternoon, Karima Begum. Am I audible to you? Can you able to see my screen? Just let me know in the chat box if you can able to hear me and see me. Yes, fine. So now let's go with the session, okay? So we are dealing with. Good afternoon, my dear. Good afternoon. Very good afternoon. So shall we start the class? Are you ready? All right. So, yeah, we are dealing with the haloalkanes and haloarenes, right? So in the previous class, I have started this with the nomenclature, classification, and some introduction part of this haloalkanes and haloarenes we have seen. And at last, we have completed the session with the nature of CH bond, right? So in today's session, we are going to look into the preparation of haloalkanes and haloarenes. Okay. So once we complete this preparation, then if time permits, we can go for the properties. All right. So now taking into the topic preparation of haloalkanes and haloarenes, the learning objectives under this topic are the preparation of haloalkanes from alcohols, preparation of haloalkanes from alkanes, preparation of haloalkanes from alkenes. So these are the three preparation of haloalkanes. Okay. And later on we have the preparation of haloarenes. So that we will do separately. So first let's go into the preparation of these three. Okay. First let me take the preparation of haloalkanes from alcohols. So as you know that the alcohols have the general formula ROH. Okay. Alcohols have the general formula ROH. So from alcohols itself, we can prepare the haloalkanes using different ways. Okay. So the first method of preparation of haloalkane from alcohol is from Lucas reagent. Okay. So who is this reagent? What is Lucas reagent? Lucas is the name of the scientist, and that scientist introduced a reagent, okay, which is called as Lucas reagent. So the Lucas reagent is concentrated HCl and anhydrous zinc chloride. Concentrated HCl and anhydrous zinc chloride. Okay. So this is the Lucas reagent. So now we have to take the alcohol. Alcohol will react with this Lucas reagent, which is HCl and zinc chloride, and it will lead to the product RCl. Okay, which is the haloalkane. Okay. So what has happened here? The OH has been replaced by Cl. Okay, the OH group has been replaced by Cl. So that's all. It's very easy. Okay. So first of all, we have HCl, and that HCl will produce H plus and Cl minus. So to the alcohol, zinc chloride will react with it and it will form a intermediate like this. And the electron shift happens and it forms a carbocation. Okay, and we get a zinc chloride with OH. So that carbocation reacts with the Cl minus, which is present in HCl, which and it leads to the formation of RCl. Okay. So later on, the byproduct which has formed will react with H plus and it will form zinc chloride back at H2. Okay. So this is the mechanism. So you don't have to worry much about the mechanism. Okay. So the OH will be replaced by Cl. So that is the concept, that is a thing you have to keep in your mind. Okay, the Lucas reagent you should know, and the conversion of ROH to RCl you should. So that is enough. Next, coming to the second preparation. The second preparation is from sodium bromide and H2SO4. Okay. So let's take the alcohol. And the alcohol is treated with NaBr and H2SO4, which leads to the formation of RX, NaHSO4, and H2. Okay. So here OH is getting replaced by the halogen. So mostly here we have bromine halogen. So it will be replaced by bromine. Okay, let's see some example. Let, let us take one alcohol. So here I have taken ethanol, which is C2H5 and OH. Okay, so now ethanol is treated with NaBr and H2SO4 and it leads to the formation of C2H5Br. OH is replaced by the bromine. So we get bromoethane with the release of NaHSO4 and H2. Okay. So we have the same thing methanol. Methanol is treated with the same reagent. So now what will happen? We will get CH3Br and NaHSO4 with H2. Bromomethane is formed. So what is happening here? The OH is getting replaced by bromine. Okay. So we are getting the haloalkane from this reagent. Got it? Now the third method of preparation from alcohol is using PX3, where X is the halogen. So we have to take 3 moles of alcohol here and that has to be treated with PX3 and it leads to the formation of 3RX. Okay. So the byproduct will be H3PO3. And here the X is a halogen I told you, right? So that halogen can be a chlorine or bromine. It is a chlorine or bromine. It cannot be fluorine or iodine. Okay, so 3 moles of the OH is getting replaced by 3 moles of the halogen part. Okay, so now let's see some example. So let me take ethanol again. Okay, I have taken 3 moles of ethanol and I have treated this with PCl3. So what will be the product? It will be 3 moles of C2H5Cl with H3PO3. Okay, with the H3PO3. So if I take methanol and if I treat it with PBr3, I will get 3 moles of CH3Br with the release of H3PO. Got it? So you need to memorize the byproducts which we are getting from the each reagent which we are using in all the reactions. Got it? So in all the cases, the OH is getting replaced by the halogen. If I take PX3 type, the halogen should be chlorine or bromine. Okay, if I use PX3, what is the byproduct? It is H3PO3. So like that, you have to memorize the reagent and the byproduct you are getting from the reactions. All right. Now the fourth method of preparation is from PCl5. So I'm taking the ROH. ROH is treated with PCl5 now. Now, chlorine is the halogen. So obviously the OH will be replaced by chlorine. OH will be replaced by chlorine. Okay. And the other byproducts will be POCl3 and HCl. POCl3 and HCl. So the examples are take an ethanol and treat it with PCl5. You will get C2H5Cl, POCl3 and HCl. So if I take some other alcohol, if I take propan-2-ol, so this is a 3-carbon system. So it should be numbered 1, 2, 3, right? So 3 carbon means it is propane. And in the second carbon, I have the alcohol. So it is propan-2-ol. Propan-2-ol is treated with PCl5. So what will be the product? It will be CH3, CHCl, CH3. I mean the OH will be substituted by the chlorine halogen here and the POCl3 and HCl are the byproducts. Okay. This is the fourth method of preparation. Now coming to the fifth method. It is by using red phosphorus and halogen. It is by using red phosphorus and halogen. Okay. So take an alcohol, treat it with red phosphorus and halogen. So the OH group will be substituted by the halogen. Okay. So I will get RX. And here the halogen should be bromine or iodine. So this X is a halogen, right? So X should be a bromine or it should be a iodine. Okay, it cannot be the some other elements. So coming to the example, if I have an alcohol, ethanol, if I try to treat it with red phosphorus and chlorine, what will be the product? Will be C2H5 and Cl, and that's it. This is called as chloroethane. Since we have two carbons, it is ethane. So it is chloroethane. So this is the fifth method of preparation from alcohol. Now coming to the last method, which is the sixth method, that is from SOCl2. So this is the best method to prepare the alkyl halides or haloalkanes. Okay. So I'll tell you why it is the best method. So first of all, let me take an alcohol and treat it with SOCl2. So here we have Cl as the halogen. So the OH will be substituted by Cl. So finally, I will get a chloroalkane with the release of SO2 and HCl. So here, both sulfur dioxide and hydrogen chloride, both of them are the gases. Okay. So in the reaction mixture, I will have RCl, I will have SO2, and I will have HCl. Since these two are the gases, they will go out, they will get evaporated from the container, and we are left with only the RCl, which is the desired product in the container. Okay, so that's why this is the best method to prepare. I mean, you can get the haloalkane which you want so easily from this method. In other methods, you have to use some separation techniques to separate the byproducts. In all other methods, some other byproducts were formed, right? So we have to use a separation techniques to separate the haloalkane from the byproduct which we got. So it will take some time. So to avoid that, to get the haloalkane easily in a less period of time, so we can go for the sixth method of preparation. Okay. So these are the 6 methods of preparation of haloalkanes from alcohols. Okay. So I hope it is clear. Now let me go for the second method of preparation. So it is from alkanes. The second method of preparation of haloalkane is from alkanes. So what are alkanes basically? They are the hydrocarbons. Okay, they are the hydrocarbons with the carbon-carbon single bond containing systems. All right. So now the first method from alkane is by free radical halogenation. So how do we get a haloalkane from the alkanes? Using this free radical halogenation. So let me show you the general reaction first. As you all know that the general formula for an alkane is CnH2n plus 2. So this is the general formula for an alkane. Suppose if I have n value as 2, what will be my product? What will be the alkane? It will be C2, 2 into 2, 4, 4 plus 2 is 6. So I will have C2H6 and let me take the halogen as chlorine. Okay, it is treated with chlorine in presence of sunlight. Okay, this H nu is a sunlight energy, light energy, which is coming from sunlight. And it will lead to the formation of haloalkane and HX. So you see the formula here. N value is 2. When 2 into 2 is 4. 4 plus 1 is 5. So it will be C2H5Cl plus HCl. So we are getting an haloalkane. Chloroethane I am getting from ethane. Okay. So this is proceeding through free radical chain mechanism. So free radical chain mechanism means it will take 3 steps. Okay. It proceeds through the following 3 steps. In the step 1, it is called as initiation, and the step 2 is called as propagation. Step 3 is called as termination. So first we will start the process, then we continue that, then we stop it. So that is initiation, propagation and termination. So through these 3 steps, we are doing the free radical halogenation in presence of the sunlight, and from that we are getting the haloalkane. Okay. So you should know that if H nu is there, then the reaction would have proceed through this free radical chain mechanism only. Okay. So this is the preparation from alkanes. Now let's go for the preparation from alkenes. So I have taught you the preparation from alcohols, and also we have completed the preparation from alkanes. And thirdly, now we are going to see the preparation of haloalkane from alkenes. So from alkenes, what are alkenes actually? Alkenes are carbon-carbon double bonded containing system. Okay, carbon-carbon double bond containing system. So from that we are going to find out. So under this, the first subcategory is called as addition of hydrogen halide. So what is hydrogen halide? Hydrogen and halogen containing compound like HCl, HBr, etc. Okay. So take an alkene. What is an alkene? It is a carbon-carbon double bonded system. And to this alkene, HX is treated and with the presence of CCl4. CCl4 is just a solvent, okay? It is just a solvent. So that will not take part in the product. So it is just a solvent. So we will get a product like this. So how did we get this product? We have to break this bond. And from this HX, add H to one carbon and X to the other carbon, so that we will achieve this product, which is an alkyl halide. Okay. So now let's see one example. So I have taken ethene. Ethene means a two carbon containing alkene. CH2 double bond CH2. So to this, add HBr in presence of CCl4. So what will we get? We have to break this bond. Since this alkene is a symmetrical alkene, symmetrical means if I cut this molecule into two with respect to the double bond, I will get two equal half. So those molecules are called as symmetrical molecules. So since ethene is a symmetrical molecule here, I have to break the bond and I have to add H to one carbon and the bromine to the other carbon. By doing so, we will get the product like this. We will get CH3, single bond CH2, single bond bromine. Okay, bromoethane. This is called as bromoethane. And let me take one more example, which is a symmetrical alkene. But2ene. So 1, 2, 3, 4 carbon, right? So since it is a 4 carbon system, it is called as but. And between second carbon and third carbon, we have a double bond. So it is 2ene. Okay. Ene represents the carbon-carbon double bond. So if I treat this with HBr in presence of CCl4, what will I get? I will get a haloalkane. So what I have to do? I have to break this bond, add HBr to one carbon and the Br H to one carbon and the Br to the other carbon. So we will get the product like this. Got it? So let me number the carbon. 1, 2, 3, 4. And to the second carbon, bromine is attached. So it is called as 2-bromobutane. Okay. So these alkenes are actually called as symmetrical alkenes. And we are adding the H and Br in the way which we want. Okay. You can add H and Br in the other way around also. You will get the same product. Okay. But instead of symmetrical alkenes, if I have unsymmetrical alkenes, unsymmetrical means if I break the molecule with respect to the double bond, I will get unequal halves. Okay. So if I get a molecule like that, the very simple example is propene. So if I cut this molecule into two with respect to the double bond, I will get two unequal half, right? So here and here both are different. So it is an example for unsymmetrical alkene. Now, if this unsymmetrical alkene is treated with HBr, H plus and Br minus, we will get two different products. Okay, we will get two different products. So the double bond will go and attack the H plus and the electron will be shifted towards, actually here it is delta minus, okay. This delta minus because bromine is electronegative. Electrons will move towards bromine. And we get a carbocation. Okay, carbocation, two different types of carbocation we get. Okay. So if this hydrogen goes to this particular carbon, the first carbon, I will get the, let me take this as 1. So this is product 1. Okay. And if the hydrogen goes to this carbon, okay, this is the second intermediate. Okay, I will get two different types of intermediate from this reaction. So one is the secondary carbocation. Secondary means if I have positive charge in CH, it is secondary carbocation. If I have the positive charge in CH2, then it is called as a primary carbocation. So among secondary and primary, which is more stable? Secondary carbocation is more stable compared to the primary carbocation. Okay. So actually tertiary is more stable, then comes secondary, then comes primary. So here we have only secondary and primary. Secondary is more stable compared to primary. Now with these intermediates, the Br minus will come and react. Okay. So the negative charge will come and attack the positive charge, right? So if they attack the carbocations, we will get the products accordingly. So in the first case, bromine is attached to the second carbon, and here it is attached to the first carbon, in which the positive charge is located on the carbon. Okay. So now out of these two, one will be the major product and the another one will be the minor product. Which one is the major product? The first product. First means the product which has formed from the secondary carbocation formation is the major product. Okay. And the other one is the minor product. So we call this as the Markovnikov's addition. Okay. Markovnikov's addition. So what is meant by Markovnikov's addition or what is Markovnikov rule? It is the hydrogen or the electrophilic part. Electrophilic means the positively charged containing part. Okay. Attacking molecule gets attached to the carbon which has more number of hydrogen atoms. The hydrogen or the electrophilic part of the attacking molecule gets attached to the carbon which have more number of hydrogen atoms. Okay. Let me take one more example. I have taken the propene. So here, this is the double bonded system. Okay, double bonded carbons. So in the middle carbon, only one hydrogen is attached. And to the terminal carbon, we have two hydrogens attached. And the attacking molecule is HBr. And the hydrogen is the partially positively charged species and bromine is the partially negative charged containing species. Now, what does this Markovnikov rule says? For unsymmetrical system, the hydrogen or the electrophilic part of the attacking molecule goes to the carbon which has more number of hydrogen. So, in the terminal carbon only, we have more number of hydrogen. So, this hydrogen will go to this carbon and the bromine will go to the middle carbon. Okay. I will get a product like this and this will be the major product. Got it? So this Markovnikov rule is applicable for unsymmetrical system. Okay. For unsymmetrical alkenes, we have to follow the Markovnikov's rule for the addition of HBr. Just simply we cannot add H and Br to the carbon which we want. Okay, we have to follow this rule. So the hydrogen has to go to the double bonded carbon which has more number of hydrogen. Okay, the other one will go to the less number of hydrogen containing carbon. All right. So this is how we get the major product using this rule. So can you able to understand the Markovnikov rule? Vishan, is Markovnikov rule clear to you? Shall I go for the anti-Markovnikov rule? Do you have any doubt here? Okay. Fine. Now let's go for the anti-Markovnikov addition. It is just the opposite. In case of Markovnikov, the hydrogen went to the carbon which has more number of hydrogen. Anti-Marconic means the hydrogen will go to the less number of hydrogen containing carbon. Okay. So this will happen in presence of peroxide. In the presence of peroxide, addition of HBr to unsymmetrical alkenes, we are attached to that carbon which has more number of hydrogen atoms. So let me take an example so that you can understand this better. So this is the example. Okay, unsymmetrical alkene example. And the attacking agent is HBr. So now we have to look into the double bonds. Okay. So the last carbon has 2 hydrogen and the middle carbon has 1 hydrogen. Now, including to this, we are going to add the peroxide. Benzoyl peroxide. Okay, very important peroxide. C6H5CO twice and O2. This is a benzoyl peroxide. In presence of peroxide, anti-Marconic addition happens. It means the positive part of the attacking molecule will go to the carbon which has less number of hydrogen. Okay. In Marconic, it went to the carbon which has more number of hydrogen. Now it is going to the carbon which has less number of hydrogen. Just the opposite. Okay. Very easy. And the bromine will go to the carbon which has more number of hydrogen. So we will get a product like this. Okay. C2H5, CH2, CH2, Br. So it is numbered 1, 2, and here we have 2 carbon, right? So third carbon, 4 carbons are there. So it is 1 bromobutane. 1 bromobutane. So this is also called as peroxide effect or Karash effect. Okay? Peroxide effect or Karash effect. So it happens only with the addition of HBr. Okay, it will not work with HCl or HI or HF. Okay, so these 3 hydrogen halides cannot be used. Means there is no effect on addition of these 3 reagents with the peroxide. It has the effect only with HBr with peroxide. Only HBr with the peroxide follows anti-Marconic addition. Okay, so under alkenes topic, the addition of halogens is getting over with this. The next is the addition of halogens. First is the addition of hydrogen halide, and in that hydrogen halide addition, we have studied 2 rules. One is anti-Marconic and the other one is Marconic. Now let's go for the addition of halogens. So take an alkene, add halogen in presence of CCl4, you will get the vicinal dihalide. So the halogen can be chlorine or bromine. Okay, you have to break the bond, add chlorine. Both of them are halogens, right? So if I have chlorine as the halogen here, I have to add the 2 chlorine like this. If I have the bromine, then I have to add the 2 bromine by breaking the double bond. Okay, so at the end, I will get the vicinal dihalide. So what is meant by vicinal dihalide? If the 2 halogens are attached to the 2 adjacent carbon, if the 2 halogens are attached to the 2 adjacent carbon, then it is called as vicinal dihalide. Okay, vicinal dihalide. So let me take one example. Let me take CH3, CH2, CH, double bond, CH, CH3. Okay, so this is one example. And to this, I am going to add Cl2 in presence of CCl. Okay, so what I have to do? I have to break this double bond and I have to add 2 chlorine like this. So what will be my product? It is CH3, CH2, CH, Cl, and here we have CH and Cl, here CH3. Okay, so to the adjacent carbons, we have 2 chlorines, which is called as vicinal dihalide. Okay, vicinal dihalide. This is the method of preparation of haloalkane, especially the chloroalkane and the bromoalkane from alkenes. Okay. So far we did not prepare the fluoroalkane and the iodoalkane, right? So we have some special methods to prepare those two type of haloalkane, and we call the name of the method as halogen exchange method. Okay. So under this topic, we have two reactions. Okay. This topic is mainly to prepare the fluoro and iodoalkanes. Got it? So fluoroalkane reaction is two reactor, and the iodoalkane preparation is very slow. So we could not prepare those two haloalkanes using the normal methods which we have used for the preparation of chloro and bromine. Okay. So to prepare the other fluoroiodoalkanes, we have to use some other method, okay, which is called as halogen exchange. So the first reaction under this is called as Finkelstein reaction. Finkelstein is the name of the scientist. Okay. So you have to take some haloalkane and it has to be treated with NaI in presence of dry acetone. The name says that it is a halogen exchange reaction. So what will happen? The one halogen will be exchanged by the other halogen. Okay. So we will get Ri and NaX. So here we have X, and that X could be chlorine and it should be bromine. Okay. So for example, if I have CH3Br, which is bromomethane, and if I treat this bromomethane with sodium iodide in presence of acetone, what will I get? I have to replace this bromine by iodine. So what will be the product? It is CH3I and NaBr. Okay. So very simple and easy and very important reaction. Finkelstein reaction. So how do we know that this particular reaction is a Finkelstein reaction? By looking into the reagent, sodium iodide. So sodium iodide indicates that the given reaction is the example for Finkelstein reaction. Okay. All right. Shall I go for the second type of reaction under halogen exchange? Any doubt so far for anyone? Okay, fine. Now let's go for the second type of reaction, which is called as Schwarz reaction. So here also we have to take some haloalkane with the chlorine or bromine in the reactant, and it is treated with the fluorine containing source. Mainly here it is in silver fluoride, AgF, and we have to heat it. So now the bromine halogen will be exchanged by the fluorine. So what will be the product? It is CH3F and AgPr. So the fluoroalkane is prepared. So in the previous case, we have prepared iodoalkane, and here we are preparing the fluoroalkane. Okay. The fluorine containing source cannot be only the silver fluoride. We also have some other fluoride containing source. So those compounds are Hg2F2, COF2, SbF3. Okay. So these three reagents can also be used in the place of AgF. So basically, all these are the sources of the fluoride ion from which we are preparing the fluoroalkanes. Okay. So this is all about the preparations of haloalkanes. Okay. So there were three preparation. One is from alcohol, second is from alkane, third is from alkenes. And finally, we also studied about the halogen exchange reaction. All right. So now let's go into the preparation of haloarenes. So we are going to prepare the aromatic, haloarenes, aromatic halides. Okay. So the first method is from hydrocarbons by electrophilic substitution method. So let me take a hydrocarbon, aromatic hydrocarbon. The very simple example is toluene. Okay, toluene. So toluene contains only carbon and hydrogen. So it is an example for hydrocarbon. Okay. So if CH3 is attached to the phenyl ring, it is called as toluene. Okay. To this, we have to add a halogen in presence of AlCl3. So this is the electrophilic reagent. This X2 and AlCl3 is the electrophilic reagent. So mainly this X will be chlorine or bromine, etc. Okay. And from this reagent, the electrophile will be generated. And the electrophile that is generated is X plus. If it is chlorine, it is Cl plus. If it is bromine, it is Br plus. Okay. And that electrophile will go to the ortho position and para position. So what is meant by ortho position? So this is the group which is attached to the phenyl ring. The two adjacent positions are called as ortho position. Adjacent means ortho. Alternative. Alternative position means meta. Opposite position means para. Okay, so what I have said, the electrophile will go to either one of the ortho position and the para position. Okay, so I will get ortho halotoluene and the para halotoluene. Got it? So this is the first method of preparation of haloarenes from hydrocarbons. Okay. Now, secondly, we can prepare the haloarene from amines also. And this reaction is called as Sandmeyer reaction. This reaction is called as Sandmeyer reaction. So let me take the amine, aromatic amine. The very simple example for aromatic amine is aniline. So the formula for aniline is C6H5NH2. I mean the phenyl ring which is attached to the NH2 is called as amine. Okay, so this is aniline. So first of all, actually we have two steps here in the Sandmeyer reaction. Okay, so the first step is the treatment of this aniline with NaNO2 and HX. Treatment of aniline with NaNO2 and HX. And this mixture is called as nitric acid mixture. And the job of this mixture is to convert this NH2 group into N2X group. Conversion of NH2 to N2X group, which is called as benzene diazonium halide. Okay. And this benzene diazonium halide is treated with copper salt, some copper halide salt. It can be Cu2Cl2 or it can be Cu2Br. Okay. Now the halogen which is there will come and substitute the phenyl ring here, and the nitrogen gas will come out. It will get evolved out. So this is an example for Sandmeyer reaction. Okay. So let me take one example so that you can understand this better. So this is the aniline. Okay. This is the aniline. And if I take NaNO2 and HCl, I will get C6H5, N2 plus and Cl minus. And if this benzene diazonium chloride is treated with Cu2Cl2, I will get C6H5, Cl plus N. Okay, so chlorobenzene, halobenzene, haloarene is formed by Sandmeyer's reaction. Okay, so under the preparation of haloarenes, we have only two reactions. One is from hydrocarbons and the second one is from amines. Okay, let me summarize the preparations. So first of all, we have studied the preparations of haloalkanes. So there were three main categories. So first main category is from alcohol. And under alcohol, we had 6 preparation. The first one is from Lucas reagent. HCl and zinc chloride are the Lucas reagent. And the second is from NaBr and H2SO4. third is from PX3, fourth is from PCl5, fifth is using red phosphorus and halogen, sixth is from SOCl2. Okay, so in all the cases, one of the reagent will be the alcohol. The other reagent will differ. Okay, the other reagent will differ and it will lead to the corresponding products and the byproducts. Okay, so this is the first main category under the preparation of haloalkanes. The second main category is from alkanes. Under alkanes, we studied only one reaction in which the alkane has to be treated with halogen in presence of sunlight, leading to the formation of haloalkane. Okay, so this is the second method of preparation. Third category is from alkenes. So under alkenes, we study two reactions. One is using HCl, HX, using hydrogen halide. Okay, hydrogen halide. The other is using halogen. Okay, one is using HCl, HBr, etc. The other one is using Cl2, Br2, etc. Addition of hydrogen halide and addition of halogen. So these are the two reactions under alkenes. And finally, for the preparation of fluoro and iodoalkanes, we have used halogen exchange reaction, in which the first is the Finkelstein. Finkelstein will give iodoalkane with the NaI, and the Schwarz reaction will give the fluoroalkane with AgF and some other fluorine containing source. Okay, so these are the methods of preparations of haloalkanes we have studied. Then later on we have studied the method of preparation of haloarene. So the first one is from aromatic hydrocarbon, okay, where we get an electrophile. That electrophile will go and get substituted in the ortho and para. And secondly, we have studied the Sandmeyer's reaction, right? So this is from amines. Amines using Sandmeyer reaction. So in which the nitrous acid mixture is used and it will convert NH2 to N2X, and later on it is treated with copper salt, leading to the formation of the haloarene with the release of N. Okay. So this is all about the preparations of haloalkanes and haloarenes. Okay. So do you have any doubt from here? Do you have any doubt from here? Is everything clear and okay? The next topic is the properties of haloarene, alkanes and haloarenes, in which we will have chemical properties and physical properties. So first I will discuss the physical properties. Physical means appearance, mass, density, etc., melting point, boiling point kind of thing. And later on we will study the chemical properties in which all the chemical reactions will involve. Okay. So we will take the haloalkane and haloarene. We will try to do many reactions in that haloalkane and haloarene. So that is the chemical properties of haloalkanes and haloarenes. Okay. So we will do the properties in the next session. So do you have any doubt from today's session? Vishan? Do you have any doubt from today's class? Okay. Okay, I am launching a poll. You can give your feedback over there and then you can leave the class. Okay. So thank you so much for attending. Thank you. See you in the next session.